So if you found that your solution is diverged, then you use lambda less than 1. If it's converged and you want to have a faster rate to get more accurate result, then you choose the overcase, which is lambda within 1 to 2. So if let's say you don't want to apply this, you can let it to be lambda equal to 1 because there is no effect. Okay. Lastly, you should be able to find out or determine the second variable. Okay, why is second variable? So for the heater plate, it will be the heat flux denoted by the Q, and also the direction for the heat flux, okay, angle. So that's all. Thank you. In conclusion, you should be able to recognize the difference between elliptic, parabolic, and also the hyperbolic PDE. So previously, you must recognize you can use the b square minus 4ac. If let's say less than 0, okay, it will be the first case, equal to 0 or greater than 0. The important characteristic for the elliptic case is time invariant. So which means not change with respect to time, or we can call this as steady state. So next one is the parabolic PDE, which is time variant. So which means that it's transient and it can change with respect to time. Lastly, hyperbolic is also transient, can change with respect to time, and this one is oscillating as well. Okay, but for the parabolic is non-oscillating. Secondly, you must know how to derive the Laplacian difference equation from the Laplace equation. So this is about mathematical modeling. By using the numerical method. For example, if let's say you have a Laplace equation for a 2D problem, so by using some numerical differentiation, okay, you can substitute the delta square t over delta x squared here, as well as delta square t over delta y squared here, to find the t function with respect to ij. So for the heater plate, we show that we can obtain the numerical solution like this. So this is the numerical mathematical model. So if we are able to solve using this, we are able to obtain the temperature distribution for the heater plate. Next, you should be able to recognize that, okay, if we ask you to solve it using Lippmann method, it's exactly equal to you apply the Gauss-Seidel method in PDE. Just the name is different, but the approach is the same. So you must also know how to apply the Lippmann method and also the relaxation method. In this case, let's say you want to find the Tij. So in Lippmann method, first of all, you let it to be 0. Okay, before the iteration, you assume all the temperature is 0. Then you continue to find the temperature at different points by using this equation. So for the relaxation, okay, we have the oval type. So why we need this? So to make the iteration needed lesser and faster. So to do this, we make the lambda to be approximate less than 2 and within 1 to 2. Okay. So if you select the lambda to be 1, okay, it has no effect. Okay. So basically it's like you perform using this step, okay, without using the equation for realization. So if you select lambda equal to 1, it's the same effect. But if you select lambda less than 1, okay, is the is to be the under the realization case.